Hey guys, so today we're going to start gas laws. First thing you need to know about gas laws is pressure and what pressure is. So pressure is a force exerted by gas molecules as they hit the surfaces of their container. So particles are always in motion, so they're going to hit the surface of the container, whether it's a wall, a lid, whatever that may be. They just push against the wall of their container and that creates pressure. Okay, so there are lots of different things that we talk about with pressure. We talked about it when we did solutions. We talked about it, maybe you heard about it when the storms came through. And they talk about the pressure in the system, things like that. Okay, pressure also allows us to use straws efficiently. It also allows vacuums to work, things like that. Pressure is very important. So the next thing you need to write down is kinetic molecular theory. So that's just a set of rules, essentially, that predict the behavior of gases under certain conditions. And we'll get to those conditions later on in this chapter. The kinetic molecular theory does have 4 things you will need to write down. You will definitely want to pause me as we're going through this so you can make sure you get it all written down. Okay? So you can write down these ones, or you can write down the next slide. I would say probably at this point, go ahead and pause. When you're done writing, unpause, and I'm going to go ahead and discuss them. So, as you know, all particles are in motion all the time. Also remember, maybe from 8th grade, maybe from 5th grade, Newton's law says that objects move in a line until their motion is changed. So normally they're hit by something else. So gas particles are just the same as every other type of particle. They just move in straight lines until they don't anymore. So one is kind of like constant random motion, and that motion is straight until it hits something and bounces off. Number 2 is gas particles don't attract or repel each other. They don't interact at all. This is just like balls on a billiard table or a pool table. I know some of y'all play 8-ball. So those balls really just bounce off of each other and keep going. They don't lose too much energy, things like that, to a different ball when they hit. Okay, so we just say they don't interact with each other. 3, lots of space between gas particles. That's something you should know already. And the size of the gas particles themselves are so small in comparison to that large amount of space that's between them. Because remember, gases take up they don't have to take up lots of space, but they can take the space of any container per se, which could be this room we're in. It could be anything. And the 4th one is that the average kinetic energy is directly proportional to the temperature in Kelvin. Now, it is important that you know that it's Kelvin, and we'll talk about that next class. But that does mean as temperature increases, so does the particle energy. Now, you also need to keep in mind that kinetic energy is directly related to speed. Speed is one of the parts of kinetic energy. So as temperature increases, so does the speed of the particles. You could kind of think about that like lizards or other cold-blooded animals. When it's really cold outside, those animals don't move very quickly because they're cold. Okay, as the temperature heats up, those cold-blooded animals will start to move around, and eventually, they'll start moving faster as it gets warmer. So that's what the particles do. Again, if you still need a pause, please do so, and then unpause when you're ready. Okay, kinetic molecular theory is also consistent with normal properties we know of gases. So if you need to write these down, you can. However, we've talked about all of these properties more than one time. So if you've forgotten, please write them down because they could be on a test. So gases are compressible. Remember, that means we can squish them down into a smaller space. However, liquids are not, and neither are solids. Only gases are compressible. It's because there's lots of space between their particles. Remember, that's postulate 3. Gases also assume the shape of their container. They also take the volume of their container. So gases will spread out in their container evenly. And remember, they're in constant random motion. They're moving around their container, but they take the shape and the volume of their container. It's postulate 1. And you should know that gases have low densities. You should just kind of know that. In fact, gases have such low densities that in comparison to a liquid, if I had a can of soda, it would take about 1,700 cans of gaseous soda to make that one can that was liquid with the same amount of stuff, just because gases spread out so much and have such a low density. So those are things you should know, but if you need to write them down, please do. Next thing we're going to be talking about is, as we go through the types of pressure, we're going to talk about some real-world applications to pressure. One of them being the pressure in your ear. You know, if you get on a plane, or even if you drive up a mountain, or just kind of a tall hill, like my ears sometimes pop in hill country in Texas, you know, down by like Austin. Not always, but sometimes. So just that differential in pressure makes your ear have this imbalance in it, and when that happens, the ear wants to equalize the pressure inside the ear and outside the ear, so it pops to relieve that pain. Okay. So now we're going to talk about the different units of pressure. This is what the 2 first mastering chemistry questions are on. So when we're done with this video, you can answer the first 2 mastering chemistry questions. So the SI unit for pressure is called a Pascal. And 1 atmosphere is equal to 101.325 pascals, or 101.325, sorry, that was kilopascals. Just regular pascals is times 1,000. Because remember, kilo is bigger than regular units. Okay, so make sure you know those. Those are part of the pressure conversions we're going to go through. Everything we talk about in the pressure conversions is related to 1 atmosphere. That is the standard pressure at sea level that we use for chemistry. Now, while the SI unit is a Pascal, in chemistry, our standard unit is the atmosphere, or ATM. The next unit we're going to talk about is millimeters of mercury, or inches of mercury. So millimeters of mercury is how we originally used a barometer, kind of like mercury used to also be used in thermometers. A barometer measures pressure. Okay, so in many countries, they use the metric system, which is why they would measure in millimeters of mercury. In America, we use the imperial system, so we would measure in inches of mercury. Okay, so you need to know both these conversions. 1 atmosphere is equal to 760 millimeters of mercury, which is also equal to 760 torr, because they're the same equivalency, and it says that they're below 1 millimeter of mercury is equal to 1 torr. Torr was the scientist that invented the barometer, so they got to name a unit after themselves. Some ones we use in the imperial system are these 2. Now, while they are not read, you need to use them for mastering, and we're going to use them in these examples. So if you want to write them on your periodic table, you can. If I put them on the test, though, those 2, I will give you those values. So remember, every one of these pressure units is equal to 1 atmosphere. Here's just a slide that gives you all the different common units of pressure. So now we're going to go ahead and convert. We're going to look at this one. I'm going to work a problem, and then ideally you will work 2 problems. Okay, so we're going to convert 0.311 atmospheres to millimeters of mercury. We'll take our given, we'll divide it by atmosphere, so our units cancel. Then we'll multiply by 760 millimeters of mercury to get 236 millimeters of mercury at the end. So here's our question that I'm going to work with you. We've got 125 psi, And we need to know what the pressure is in millimeters of mercury. I'm going to say 125 psi to mmHg. You need to go back, if you need to go back, it's on slide 22 where all the unit conversions were in that little table. Okay, so always start with your given psi. Remember, psi has to go at the bottom, and all units are related to atmospheres. So 1 atmosphere. We go back and look at the table. 14.7 psi is equal to 1 atmosphere. Psi cancels, but atmospheres is not what I want. I want millimeters of mercury. So I go on. 1 atmosphere is equal to 760 mmHg, which again stands for millimeters of mercury. Atmospheres cancel, and then we're there. Generally, you will have to go through atmospheres, so you will generally need 2 conversions for pressure conversions, unless it gives you atmospheres or asks for atmospheres. So keep in mind, we do need to look at sig figs. There's 125 psi, which is 3 sig figs. So we're looking at 6460 millimeters of mercury. Because of sig figs, I understand the calculator should say 6462. All right, let's look at another problem. I'm actually going to work this one with you too, and then you're going to work the next one. So this one wants us to convert inches of mercury into pounds per square inch. Again, go back to slide 22. It's on there for the conversions. So we're going to start with 173 inches of mercury. There are 29.92 inches of mercury in an atmosphere. So again, remember, units have to cancel. Then we're still using atmospheres, is equal to 14.7 psi, which is the same as pounds per square inch. Hopefully you know in America we use pounds per square inch most commonly for tire pressure, which everybody should be able to check their tire pressure once they're driving. All right, so when I do this math, I get 84.996. We need 3 sig figs, so this is equal to 85. It rounds up to 84.99, but because I need 3 sig figs, it has to be 85.0 psi. Okay. This problem, I want you to go ahead and do that problem and then submit it, and then make sure you work on mastering. There are 2 questions. If you have any questions, please reach out via Remind. All right, y'all have a great day.